So I'm going to talk about building modular Parsl workflows in Parallel Works. And in this tutorial, I will show some examples and best practices that we use in Parallel Works to build modular workflows. So first, I will briefly explain what workflow is in Parallel Works. Then why we want to build modular workflows and how to do it. And I will show two examples, the script CSV and the pipeline example. And finally, if I have time, I will talk about wrapping Parsl apps. And so another simple example, the simple pass runner. So when we say Parsl workflow, we refer to a bunch of Parsl scripts with defined inputs and outputs that have some Parsl apps that are executed on remote resources. And in Parallel Works, we encapsulate these scripts into a workflow or app, and you can use the platform to develop, execute, and share these workflows. Not going to say much more about the platform. So now let's talk about making these workflows modular and what I mean by modular. So typical workflow in Parallel Works is shown here in this slide. For example, the converts runner is a good example. It takes some input files, stages them to a remote machine where it runs the convert CFD code. And when the simulation is done, it produces some results that are then staged back to the platform. And sometimes you would want to post-process these results with another workflow. For this, you can use the Paraview post-processor workflow that will take these results and extract metrics, images, and animations. So sometimes you want to run and post-process in the same workflow. And the way we did this before was by creating a third workflow and then copying and editing blocks of code from the previous two workflows into the third. And you can see here, I'm showing an example called converts Paraview runner. When we call a workflow runner, we typically mean that it only runs one case, just a side note. So the advantages of doing this is that the workflow is self-contained, but the disadvantages are many. Basically, it's hard to maintain. You end up having too many workflows. If something changes in the converts runner, you have to propagate the change to the converts Paraview runner, and copying and editing blocks of code is not that fast. Also, what if you want to use a different tool? So instead of converts, you want to use OpenFOAM, which you can also post-process with the same PV post workflow. You will end up with yet another workflow, in this case, the OpenFOAM PV runner workflow. And it can get even worse if you consider different workflow topologies. So typically, we will want to run many workflows in parallel and merge the results. This is what we call a sweep. And in this in the slide, I'm showing what would be a sketch of the sweep CSV that I will talk more about later on. It takes a CSV file, splits every row represents a case, so it generates the input for all the, in this case, converts Paraview runners, executes them in parallel, waits for the results, and merge them. If you keep doing this, you end up with one workflow for every compatible software tool and workflow topology. So to avoid this, you can create a pipeline workflow that basically imports any given workflow, in this case, the converts and the Paraview post-processor, and pipes them together. And then you can pass this pipeline workflow to a sweep CSV workflow that executes many pipelines in parallel. So the solution then is building workflows as Python modules that can be imported by other workflows. And in the rest of this section, I will talk about how to actually do this. So every workflow in Parallel Works has a main.py script, and the key to make workflows modular is to create a main.py script that can be either executed directly or imported by other workflows. And by executed directly, I mean when you go to the platform, you select workflow, then you select the inputs for this workflow in the input form, you select an output directory where the results will appear, the computational resource that you want to use, and you hit the execute button. So, So when you do this, the platform is going to run a Python main command, and the workflow is going to run in a sandbox directory, a job directory that is created for it. It is going to get the input and output definitions that we saw in the form from a Python namespace that is imported here in the top of the script from the Parsl PW module. But in addition to this, now we also want workflows to be imported by other workflows. So we need to make this main.py in a particular way. So I'm showing here the 4 parts that it needs to have. The first part that I'm highlighting in yellow is the workflow function. So here you will code whatever your workflow does. For example, in the convert runner, we'll run the convert simulation. And this function is going to be imported and executed by other workflows. So you do not want to wait for features inside this function, or otherwise you won't be able to execute it many times in parallel. And then if you want this function to be compatible with the workflow builder module, which is a Python module with workflow building tools that we use to, for example, import and connect workflows, it needs to have certain input and outputs definitions. So it needs to take a Python namespace with workflow with the function input and output definitions. The reason it takes namespace is that the input from the input form is imported into the main.py as a namespace, as I mentioned before. And then optionally, you can also give it a workflow directory, and I will talk more about this later, but basically, when you execute a workflow directly, it gets its own sandbox job directory, but if the workflow is imported by another workflow, it doesn't. So if you need it, you can define it in the workflow function. And then the outputs are a dictionary of objects with a result method, where the keys are output parameter names. And the reason for this function to return dictionaries is double. First, you can easily access the workflow outputs by parameter names. And second, you can easily convert them to namespaces and pass them to other workflow functions. Okay. So the second part I'm highlighting in blue is only executed when the main.py script is executed directly. This is done in Python with the syntax if name equal main. And here you would want to load your Parsl configuration, load and pre-process your input and output definitions, run your workflow functions, and wait for the results. The third part is highlighted in green, and here this part is only imported when this part is only executed when the workflow is imported. And here you would want to build your workflow as a module. I typically don't use this part. I think I only use it in one workflow, but sometimes you need to use it. And then the rest is always executed. So I think it's better if we see it with an example. And the first example I want to show is the Swift CSV workflow topology. We're going to use it to run many times the MMS runner workflow. The MMS here stands for multimodal surface, and this is just a very simple workflow we use for testing and as an example because it runs very fast. So this is what the input form for this workflow looks like. It takes a case name. All of our workflows typically take a case name, and then it only takes one input file that is shown on the bottom left part of the slide with X and Y values. The workflow is going to calculate the Z value and write it down into another file, which is the output file. And then that file is going to be staged back to the location in red that is made basically by combining a directory that you choose in the input form with a base name that contains the case name and a timestamp. And you can see the code, the main.py for this workflow on the right. It is very simple, and it uses the simple bash runner, which hopefully, if I have time, I will explain at the end of the presentation. But this is only just defining a bash up in some particular way. And then when you execute it directly, again, it just loads the configuration and waits for the results. So the Swift CSV is going to split a CSV file into several case input files, and it's going to submit a runner workflow in parallel such that each workflow gets a case file. In this slide, I'm also showing the job directory that is created when you execute the Swift CSV workflow directly. You can see that inside that directory 55060, there is a Swift CSV directory, and inside that directory you have 0, 1, 2, 3, and so on. And those are the workflow directories corresponding to each of the MMS runner executions. So the Swift CSV input form looks as I'm showing in this slide. It takes a case name, the input parameters as a CSV file. It's this CSV file I showed before. And then the configuration file, which is the important part, that basically tells the Swift CSV which workflow to execute many times and how to connect to it. So this file has an import key where you tell it workflows that it needs to import, in this case just one. And then it has the workflow information under the runner key. It has the workflow name, MMS runner, its run function, which as you saw in this script is just run. And then you can tell it some input parameter name value separation, whether you want to exclude certain input or output parameters. And finally, the parameters of the run function. So what the Swift CSV is going to do is it's going to get these workflow parameters, make a namespace, and pass them to the run function. And you can see that the in MMS and out MMS keys are now tagged. So the Swift CSV is going to replace the value they had before by a path to these in.txt and out.txt files that you can see in the script CSV directory. And if you want to define other constant input or outputs, you can here in this section below. It's just that the script CSV is not going to change them at all. And then here I'm showing parts of the main.py script. I'm only showing parts because all of it doesn't fit. And I wanted to show that the run CSV is returning a sweep future. And the reason I'm doing this is that in this workflow, you need to wait and merge the results, but you cannot do it inside the run CSV function. So instead, what you're doing is returning this sweep future object, which has a result method that will wait for the futures and then merge them. So you can see that the run CSV function returns that future, and when the workflow is imported directly, and only then you wait for the results and merge them. And this way you can run a sweep of sweeps of sweeps without having to wait for the first one. Okay, so in the second example, I'm going to make it a bit more complicated. Here, I'm going to run again the sweep CSV around the MMS runner, but instead of passing it the input CSV file directly, I am going to pass it from our design of experiment workflows, and I'm going to connect the design of experiment workflow to the sweep CSV workflow using the pipeline workflow. The design of experiments workflow takes design space file defined as a JSON. In this case, it's just the X and Y values from 0 to 1. You will tell it which sampling method you want to use, how many samples you want, and the workflow basically returns a CSV file with all your samples and some other images and HTML files. So this CSV file with the sample design space is what I'm going to pipe into the sweep CSV, which will otherwise remain the same as in the previous example. And you can see also again a sample job directory where this workflow ran. You can see there is a pipeline directory, and inside the pipeline directory you have the design of experiments directory and the sweep CSV directory, and again inside the sweep CSV directory you have the 0, 1, 2, and so on directories that correspond to each of the MMS runner executions. So the pipeline workflow runs a list of workflows in order, piping the output of the previous workflows to the input of the next workflow, and it only waits for the required data features and returns a dictionary with the remaining data features. I'm showing the main.py on the slide. In this case, it's not very long, so it fits. And you can see that it returns dictionary with the workflow features. And when the workflow is executed directly, it waits for these features using the wait for futures function in the button. This function basically recursively goes through the dictionary searching for values that have a result method in them and executing the result method. So that's when your output txt files would be merged into a CSV file in this example. And the pipeline workflow just takes a case name and a pipeline configuration file. The format of the configuration file is the same for the sweep CSV and the pipeline, so that makes things easier. You tell it workflows that you want to import, in this case, 3 workflows: the design of experiments, script CSV, and MMS runner. And then you give it a list of workflows to execute serially. The first workflow to run is the design of experiments workflow. You can see the run function defined there and the workflow parameters. The pipeline, because this is the first workflow, is going to immediately get these workflow parameters, convert them to a namespace, and pass them to the run DOE function. And then it's going to move on to the second workflow, which is the sweep CSV. And it's going to see that the in CSV parameter of the sweep CSV is tagged with a string of out CSV. And basically any workflow parameter value that corresponds to a workflow parameter key from a previous workflow will be replaced by the actual parameter value. So the pipeline is going to wait only for the data feature that is needed for the next workflow, and then it is going to execute it. And below the workflow parameters of the sweep CSV, you find also the workflow parameters for the runner. So you can go on and build a pipeline of sweeps of pipelines of sweeps and define all the dependencies in the JSON file. Okay, so I'm very quickly going to talk about wrapping Parsl apps, because I think I've showed it in some of the slides. So I'm going to talk about the simple bash runner. There are certain tasks that you want to run every time you run a Parsl app. So these tasks you do not want to put into your workflow functions. And in the case of the simple bash runner, this runs a bash app. So what it does is it builds and runs a bash command. You can see on the right how you can define the command and some list with command arguments. So for example, the inzip is going to be replaced by the path to that file. And there are also staging conventions involved. So the simple bash runner takes care of those. It also defines the input and output as dictionaries. It streams standard output and error files from the remote machine to the local one, and you can define the stream host and a stream port. You can define a user that is actually going to execute the command, and it returns dictionary with data features. So this is the sort of things that I do for every workflow. So I put them in a bash app wrapper instead of in the workflow. So summarizing, use Parsl app wrappers to run tasks every time a Parsl app is executed. Modular workflows are built as Python modules that can be executed directly or imported. The workflow functions return features and do not wait for the results, and only wait for the results if they are executed directly. So thanks for your attention. Do you have any questions?
Very nice, Alvaro. Any questions, anyone? I was interested actually in the second part you were talking about. Seemed sort of similar to what Ben was talking about yesterday with the Join app. Is there any, I don't know if you saw Ben's, have you seen Ben's work on the Join app yet?
No, not yet.
It's Yadu is, I think,
write it down.
Ben's there at the moment, but Yadu, did you see similarities there?
Yeah, definitely. I mean, even saying that you can only wait for things in the main module is basically like sort of what Ben is trying to say in the first place. That
right. So the stuff I was working on was totally trying to address the fact that there's stuff you can only do by waiting for things in master Parsl at the moment.
Okay, I'll definitely check it.
And that's not in master branch yet, Alvaro. So I think what we'd love is if you and Ben maybe could share notes, and maybe you could have a look at what he's trying to do and see if it addresses some of your use cases or not. But it's interesting that the two of you converged on a pretty similar model there, I think, at least to my naive eyes. So it was super interesting.